Hey, thank you for joining the session of IS6, which is the invited talk given by Mr. Christos Saraziotis about the machine learning prospects for automatic SHA processing, and also the panel session J5 about innovation affecting CTBT pertinent to IDC data analysis, needs ideas, and implementation pathways. So let me move on to the first session, IS6. The speaker is Dr. Christos Saraziotis. But before giving the floor to him, I would like to introduce him to the audience. Dr. Christos Saraziotis holds degrees in mathematics and electrical engineering and a PhD in geophysics signal processing. After 10 years in the oil and gas industry, he joined the CTBTO in 2018 as a seismic acoustic officer. Dr. Saraziotis has been working on enhancing the performance of the current IDC pipeline, among other things, for aftershock sequences processing with internal and external experts, and is an advocate for machine learning and artificial intelligence in seismology and geophysics in general. Christos, you have the floor. Are you ready to start?
I am ready, yes. Can you hear me?
Yes, I can hear you.
Okay, and hopefully I shared the correct screen. Okay. So hello, thank you Noriyuki for this introduction. I will be talking about machine learning prospects for automatic SHI processing. And this is a presentation we put together with my colleagues at the CTBTO, Ron Lebras, Vera Miljanovic, and Megan Slinkard. So I will give a brief background in the beginning to put things into perspective, and then I will talk about some machine learning efforts that have been happening in the IDC and some future prospects, so some things that we would like to achieve and have already started actually working on. So first, let me give a little background to put these two big ideas, machine learning and CTBTO, into perspective. The idea of artificial intelligence was arguably born in 1950 when Alan Turing proposed his Turing test for which machines were deemed intelligent or unintelligent. And the first machine learning application was developed in 1952, and it was a checkers program that was developed for an IBM computer, and it was supposed to learn to play the game better the more it played it. From that point on, machine learning saw some development, but it wasn't as rapid as anticipated, and that led to the so-called AI winter, which was a period of reduced funding and interest in artificial intelligence research in the UK. Practically all funds were shut down.
Christos,
Yes.
Excuse for interruption, but we do not see your slide, I think.
You don't? Okay.
Yeah, now we see your screen. Please maximize the window or in the slide mode. The slide
Okay.
show.
Is this better?
Yeah, it's good. Thank you.
Okay. So, yeah, I was talking about this. In the 1970s, there was this the so-called AI winter, where practically all funding was shut down, and the term was coined by analogy to the idea of a nuclear winter. I just couldn't help but observing that, which was a severe and prolonged global climatic cooling that's supposed to occur after a large-scale nuclear war. Then in the 80s and 90s, things started rolling again.
Christos,
Yes.
we have a difficulty to see your slide. Can you send us the files now?
Okay, where should I send them?
The extract, maybe?
Should I?
Extract under SNT. Yeah, Christos.
Yep.
Can you have access to X Drive? There, you will find the folder named SMT 2021.
In Teams.
No, X Drive.
X Drive. Okay. Yeah, let me do that.
You think you can do?
In the SNT21 media, right?
Yeah.
If you could ask them to stop sharing now.
Yeah, and Christos, please stop sharing the screen.
Yes, I will. Okay, so it must be there. It's a PDF.
Yeah, the both could be PDF or PowerPoint.
It should be there already.
Okay.
Where? I got it.
Yeah, we found the file, so we want to share
Okay.
the screen outside. Christos,
Yes.
can you go token without size for a while? Or it's default then? Let's wait.
No, it's okay. I can try that.
Christos, do you see the screen?
Yes.
As you can see it, yes. Now I do not see the presentation anymore.
It was a technical problem you have.
At least since he doesn't see it.
Do you think you can also try the screen sharing on your side again?
Oh,
Okay.
share the application.
Should I share the screen?
That's it, man. This is share. Share the application. This is yes.
I'm sorry, I think on our side we are going to share the screen.
Take control. Okay.
So maybe you have the control of the slides. Can you
Um,
click?
Just click on the slide.
So I'm pressing the arrows, but
Don't click.
Once click, don't use the allow.
so I'm supposed to have control with the arrow keys, right?
No. Mouse click.
Just go
Mouse. Okay.
on the slide.
On the slide.
Yeah, that's what I'm trying to do now. But it
Okay.
doesn't seem to be working.
Okay, Christos, first you need to click the screen on the slide first.
Then you
Quit the screen.
Yeah. Then you have the control Now then you can use the arrow key. But should we control the screen on one side? Yeah, we will do. Okay, which slide do you want to show?
So I think I'm at slide 3 now.
Yes, please go to the slide 3.
No, you have to keep sharing. Else we can do it.
Well, previous one.
Yeah.
Okay, so because it's a PDF, it's not. So the previous one, please. Yes, here. Okay. So, okay, let me just continue. We're in the timeline of machine learning. And I was saying that in the 1970s, there was a big drawback because of lack of funding. But then in the 1980s and 90s, things started rolling back again, thanks to the popularization of artificial neural networks, and in particular recurrent neural networks. And also in the 90s, machine learning shifted from knowledge-driven approach to a data-driven approach, and scientists began creating programs to analyze large amounts of data and draw conclusions, learn from the results. Then in the first decade of 2000, support vector clustering and other kernel methods and unsupervised machine learning methods became widespread, and finally in the last decade, deep learning became feasible, and this led to machine learning becoming integral to many widely used software services and applications. So in this timeline, the CTBT was signed in 1996, and the routine data analysis started at the IDC in the year 2000. And this is when it was in the period when machine learning started regenerating again from its ashes, someone could say. Next slide, please. So this figure is probably familiar to most of you, but I will just give a brief overview anyway for those who are not as familiar with it. This is a sketch of the IDC processing pipeline. I think you will see it again today later. This next slide, please. The first box you see, this blue box, is corresponds to automatic SHI processing, which consists of two parts: station processing and network processing. Station processing takes place as soon as data arrive at the IDC from the individual stations, and network processing is scheduled at different times after event time. The first network processing is performed on seismic data from the primary seismological network, IMS network, and any hydroacoustic data with completed station processing. This occurs approximately 1 hour after event time. The results of this first network processing are included in cell 3, which is the first pipe that you see here. Then events in the cell 3 formed in cell 3 are used to generate requests for additional seismic data from the auxiliary seismic stations and to better locate events formed during this first phase. And the second network processing run is performed approximately 4 hours after event time. Again, and in this second run, the data are used, in addition to the previous signals, data used are signals from auxiliary data, late arriving primary seismic data, late arriving hydroacoustic data, and infrasonic data. And the product is cell 3. And then 6 hours after event time, there's a third final network processing stage, which uses all data that are available at this time, and maybe data that came late due to communication network problems, and this produces cell 3. Now, this box it's very big, and it looks like it takes a lot of time, but it doesn't. It takes just about 6 hours. Next slide, please. So now you see a very narrow strip, pink or magenta narrow strip, and this is what we call the interactive processing or analyst review. This is the most time consuming, and during the interactive review, our experts, the analysts, will review the automatically formed events and delete any false events or events that do not meet the event definition criteria, correct other mistakes during automated processing, search the data for events that have been missed by automated processing, and then they will produce a final product, which is the REB. So it's suffices to say that the better automated processing is, the faster the RAB will be produced, and the better the interactive review will be. This is why we're focusing a lot of our efforts in enhancing automated processing. Next slide. So this is, yes?
Excuse me, but we need to finish your presentation in 5 minutes. Please speed up a bit.
Is it? I thought I had until
5 minutes.
until 2:45. No?
2:40, actually.
Okay. So then I will have. Let's move on to. Let's move on to the next slide. I will just try to speed it up. So this is radionuclide and technology fusion, which will not concern us in this SHI processing presentation. Please move on. Now, there are some machine learning efforts in the IDC. Please, next slide. So this, next slide as well. So these two are some applications that have been, machine learning applications that have been used with IDC since the beginning. The first one is using neural networks to identify three-component phases. And I have a short description of this. You see that it's a very simple neural network, uses only 3 layers, input, output, and one hidden layer. And the input layer has only 15 nodes, the hidden layer 6, and the output layer only 2 nodes. And comparing to the hundreds or thousands or tens of thousands of nodes that are used today, this is like, it looks like a poor relative. Then also there was a Bayesian inference used to identify regional S phases to SN, LG, RG, and SX, unknown regional S phases as well. Next slide, please. Then again, please click. So in 2006, next slide, please, there was this symposium that had, it was actually something like a precursor, I would say, of the SNT that featured a data mining session, but it only had a couple of presentations. And in 2009, there was the International Scientific Studies Conference. Next slide. So again, please. In the ISS 2009, there was again a data mining session with about 17 sessions, I think, including phase labeling, false event identification, NetVisa, F-Detector, BaseLock, VDEC, and many more. And a lot of the presenters back then are actually still attending the conference, the SNT conference now. Next slide, please. So this is, I want to just talk briefly about 2 of these topics. The one is the generalized F-Detector, which uses prior information about the signal and noise. Next slide. And this has been tested extensively at the IDC. The code has been merged with the IDC code base, but it has not been activated for several reasons. But it is now part of the re-engineered software we're getting from the US NDC, and testing is planned for again for this year, the 3rd quarter. Next slide, please. NetVisa is also, most of you are probably very familiar with it. It uses a Bayesian approach and in the network processing step. Next slide. This is a timeline, which unfortunately I cannot go through right now. This is, but the point is here that it has been very extensively tested, and features have been added gradually and incrementally since 2013, when there was the seminal paper for NetVisa. And of course, all these features have been added. Next slide. This is an example of how NetVisa improves the automatic event list. So we see on the left, this is what the event location looks like after analyst review, but from and to the right, we see what we get with the current automatic processing pipeline. So all these events that are dispersed all over the world, then they are moved by our analysts to their correct locations. And if you move to the next slide and go back and forth, you will see what is the event list that is produced by Cell3, by NetVisa Cell3, the VCell3. So it is this pipeline is operational. It runs in complement with the current GA, which is the current global associator method, and this processing pipeline is expected to replace GA soon. Next slide, please. So I will just very briefly talk about some future prospects. Next slide. So one of the problems that we would like to solve is single station back azimuth prediction, which is not very good. It's quite poor using three component stations. You see here that especially in areas like South America, we have no array stations at all. But if you move to the next slide, we have a lot of three component stations. So back azimuth is not very reliable using three component stations, and this is something that we would like to mitigate. Next slide, please. So there was some research about this by Joshua Dickey, and I would just have to move on, but you can see a presentation about this and how we're trying to integrate it with NetVisa in the poster presentation tomorrow. Next slide, please. This is another thing that we might want to handle. We have had some presentation here at the IDC about refinement of automatically picked arrivals. So a problem is that most of the arrivals that are automatically picked, they have to be retimed by analysts, and this may not take a lot of time per se, but because there are so many arrivals, then at the end it takes like it's a very time-consuming and expensive effort. Next slide, please. And this is another issue that we would like to handle for waveform denoising to enhance the SNR of the data that are fed to the detector and associators. Please move on to the next one. And there is a list of other things that we have been talking about with their inventors and that we will be trying to maybe to do in the future. Please move on a few slides. Again, and again. So I just want to mention that there were some very nice presentations from yesterday in the oral session about the artificial intelligence and machine learning. And also tomorrow, next slide, there is a poster session. Actually, there's a poster session broken in two. Next slide, please. Again. And so I just want to finish by saying that the IDC processing pipeline is very complex. It's a very sophisticated system, and it is very difficult to integrate new methods and test them. So the vision here is that we want an environment where integration and testing of such methods will be easy. Move on, please. The solutions, we have currently two solutions. One is the VDEC, which is a platform that we use to share our data with scientists and researchers all over the world. And the second one is the containerization of the IDC pipeline, which is part of the re-engineering project. Please move on a few slides. Again. So to recap, I just had to rush through the presentation, unfortunately. We have been using, the CTBTO has been using machine learning algorithms since the beginning, and I only presented a couple of them. The presentation is not exhaustive by no means. The application of machine learning algorithms has been limited due to computational limitations in the past, but now improvements in computer hardware and have made it possible to test and use algorithms, and we have already started doing so. Mostly we are looking in enhancing the automatic processing pipeline, things that I have discussed, signal detection, denoising, phase identification and association, and other sub-processes. Another, something else would be event screening, which is also an automatic process that could be enhanced using machine learning. And we hope that with the containerization of the IDC pipeline, we will be able to simultaneously and test a lot of algorithms in the future, in the near future. Thank you for this. Thank you, and I will be happy to answer any questions if there is any time.
you, Christos. I have a small question, but you have presented some future plan or some promising algorithms in the latter half of your presentation. And my question is, are you still examining those algorithms by yourself, or it's just an introduction, what you found as the promising algorithms?
So there are two ways that we improve our let's say pipeline. One is we notice a problem that we need to solve, and others is that we see research that has been done outside, and we see if we can use it to enhance the performance of our pipeline. So some of these we have invited the inventors of these algorithms. They have presented to us, and we're planning to test them, or we've been testing them together. But yeah, so other than that, sometimes code is free in GitHub. We can download and use it. So this is also another option. But we prefer to have help from the original inventors of the methods, because they're more experienced and they know how to avoid any difficulties.
Okay, thank you. Probably audience have more questions, but we do not have enough time to discuss. But still, I believe that we can discuss his idea on the website of SNT. And those who have questions or ideas, please contact Christos on the
Please
website.
do. Please do. Thank you very much. Thank you.
Thank you very much. Let me move on to the next session, which is panel discussion. I'm still the convener, but Megan Srikar, my excellent supervisor, will be the moderator of the panel. But before giving the floor to Megan Srikar, I would like to introduce her. Megan Srikar joined CTBTO in August of 2019 and is the Chief of Software Application at the IDC. Our team is responsible for developing new innovative solutions to meet IDC needs and to develop and or integrate the software used at the IDC and distribute it to member states. Before joining the PTS, she worked at Sandia National Laboratories for 15 years. Initially as a researcher on web form correlation-based approaches for seismic monitoring, and later as the technical advisor for the ground-based nuclear explosion monitoring research program at the Department of Energy. Megan, now you have the floor, and I hope you are ready to start.
Thank you, Noriyuki, for that very nice introduction. Welcome to all of you. We have a very exciting team of panelists here today, and I think it will be a very engaging conversation in all the ways that data analysis can really enhance our capabilities here at the IDC. First, I also want to thank Christos. That was a perfect introduction to the topics of this session. Really a wonderful introduction. And for those of you that were aware of the technical issues we had with that talk, I encourage you to go back and look at it again, because he really put a lot of good stuff in those slides. Christos highlighted a lot of the key developments of this area, which we'll be talking about again. So my goals for today are sort of threefold. I want us to talk about how data analysis methods can really enhance our abilities here at the IDC. I want to talk about where the next big contributions might come from, and talk about emerging areas that could feed some of those big contributions. And I also want to make sure that you walk away with a general understanding of what the process is like, coming from an idea to the testing and implementation process at the IDC. So to help me discuss all those things, I have a fantastic set of panelists here today, which can talk about things sort of from all angles, from the seismic side, from the radionuclide side, from the experience of being through this whole long process, and from the newer researcher perspective to really talk about those emerging areas. So let's go ahead and get them to turn on their videos and allow me to introduce them. So I've got the first one popping up here is Steve Myers, so I'll introduce him first. So Dr. Myers has worked at Lawrence Livermore National Laboratories in the United States for 24 years as a research seismologist and program leader. He currently serves as Associate Program Leader for Nuclear Detonation Detection at Livermore. Many of you know him because he's been a delegate to Working Group B and been very active in the Waveform Expert Group meetings. He led the multi-institutional development of the Regional Seismic Travel Time Effort, that's RSTT to many of you, which was provided by the US to the CTBTO PrepCom and is now incorporated into the IDC. RSTT is also featured in our training and workshops. More recently, Dr. Myers has worked with computer scientists and statisticians to apply machine learning and artificial intelligence to nuclear explosion monitoring applications, including the emulation of full physics, seismic wave calculations, and seismic data analysis. If you didn't catch his talk on that yesterday, I encourage you to go back and watch that. And last but not least, he is a recipient of the 2014 Department of Energy E.O. Lawrence Award for contributions to nuclear nonproliferation. So Steve, we are super glad that you can join us today. Next, I wanted to introduce Harry Miley. So Dr. Miley joined Pacific Northwest National Laboratories in 1987. Where he developed an ultra-trace nuclear detector methods to determine the mass of the neutrino, and later to detect tiny radioactive traces of nuclear tests. He received the R&D 100 and FLC awards in 1998 for the development and tech transfer of the radionuclide arsenal sampler, which has been in use in the IMS since about 2000. Since 1998, Dr. Miley has participated in Working Group B as a member of the US delegation and attended many RNEG sessions. In 2014, he led the IFE radionuclide team of on-site inspectors. And since 2015, he has been the science lead at PNNL, researching new methods and approaches for monitoring nuclear testing. So Harry, thank you so much for joining us. We're delighted to have you. Next, I'd like to introduce Dr. Claire Labon. She received her PhD from the University of Nice, Sophia Antipoulos in 2016. After a year postdoctoral fellowship at the Institut de Physique du Globe de Paris, she joined the French Alternative Energies and Atomic Energy Commission in 2018. Her research interest is mainly in seismic signal processing, particularly for three-component seismic arrays. Her latest research achievements are about her three-component LTQ-FK analysis method, which improves the signal detection capabilities. And that was presented this morning at the 3.5 session. Next, I'd like to introduce Dr. Nima Arora. Nima received his PhD in artificial intelligence from UC Berkeley in 2012. He co-invented the NetVisa probabilistic model for building event bulletins. We'll be discussing that quite a lot today. He is currently a scientist at Bayesian Logic, which he founded in 2011. He recently held a position as research scientist at Facebook, applying statistical models to combat election misinformation. So we'll be looking forward to hearing your thoughts on what we can learn from work in other domains and applying it to the CTBTO world. Last but not least, we've got a fantastic and knowledgeable convener of our session today, and I might pull him in to answer a few questions. So I want to make sure that we have properly introduced Dr. Noriyuki Kushida as well. He joined CTBTO in 2014 as a software engineer. He has been working on scientific computing and high-performance computing with a particular focus on physics simulations. Dr. Kuchida is one of the contributors of the NetVisa project and is implementing the new SHI data processing pipeline with NetVisa here at the IDC. He has also currently developed hydroacoustic models on high-performance computers with external experts. So thank you, Noriyuki. Thank you, all of you. As you can tell, we've got a fantastic team. So I thought we would just jump right into some questions today. And of course, as we talk, please submit your questions to the chat so that we can get even more ideas of what to talk about. But I wanted to start by posing a question to, I think, Harry and then to Steve. And the first question is, where have we already seen improvements to data analysis leading to significant gains and benefits to the IDC world?
Thank you, Megan. Let me share my screen here. I'm going to show a couple of slides as part of an answer. Let's see, maybe I should show the right thing. Looks like you see my my slides. Okay, so as Noriyuki, excuse me, as Megan just said, well, I'm just blown away that Noriyuki said, my excellent supervisor. I've never heard those words together before, so Megan must be a great supervisor. Anyway, back to the point. I started in about 1992 on the RASA project, and the state of the world in monitoring was very simplistic for radionuclides at that time, nothing like the sophistication of waveform systems. You might have a single detection, and this is what I'm showing here, a few points that are above the threshold. You might take the best one and do an atmospheric backtrack and find out what continent it came from. And that's because that was so poor. And back in the day, you got multiple isotopes because we were looking at things that leaked a lot or took place in the atmosphere. We looked at isotopic ratios of a single sample to tell us everything that we could learn about an event. Now, the world has changed, and now it's much more likely that we get just a xenon detection. And so with a single isotope, what can we do? Well, there's emerging amongst lots of groups, national groups that are employing this method where we select associated detections and non-detect measurements and combine them with atmospheric transport dilution calculations in a Bayesian statistical framework to create a radionuclide event. This radionuclide event is analogous to the seismic event that the IDC currently processes, uses, reports. What we can do a lot of things with this. We can create a probability distribution, and that distribution is then ready to fuse with other technologies. So let me show you a little bit of what the power of this is. So this is a real example from April 2013. There were a series of noble gas detections at JPX 38. And if we took the single one best sample, we would create a probability distribution. That's not a dilution calculation, but this is the location probability for that. And that's in panel A. So it's from a single detect. If we add one non-detect, so that's actually very marginal information, add a non-detect, a giant lobe of probability. And I should say, everything that's green or pink is a possible location. Everything above 10% probability. Everything above 50% probability is in pink. And the darker the pink, the more likely the location. And this little pink spot that you see in the middle, sort of reddish pink that doesn't really stand out, that's the nominal DPRK test site. So if we have 2 detects or 3 detects and 2 non-detects, you see we can constrain the location further and further. So our location capabilities improve substantially. I should point out, though, if we add signals from air parcels that are not related to this, we actually get a worse answer. So you have to be very careful about what you include. And I think there's an analog there to the seismic case. So what's the impact of having a much tighter location? We might rule out a seismic origin. If the ground shook substantially far away from this pink region, you might say these are not related. It might suggest a civilian source if a well-known civilian source is in the pink region, that sort of thing. But so much more comes out of this. Once we've taken that first step and given ourselves a location and guessed at a duration and height of release like ground level, then we can take each sample and perform a number of backtracks for them and get a most likely release magnitude. And what comes out of this calculation is different than what my eye would say as an interpreter, and also release time. And there's multiple ways of doing this, but we argue about the time of release now in terms of hours, which 3-hour block was it in, as opposed to what day. So it's a huge possible improvement. And that's where I'll finish for now. And I'd like to come back later and talk more about it if possible.
Great, that was a wonderful introduction of the benefits, the progress we've made, but also where you sometimes need to be a little careful. So thank you. Let's turn it over now to Steve for his perspective more from the seismic side. I think you're muted, Steve.
I am muted. I shared my screen before I could unmute myself, and then I lost where the unmute button was. So presumably you can hear me because I see a lot of smiling. And can you see my screen? Okay, I see nodding. So I'm Steve Myers from Lawrence Livermore, as you heard. I'm going to review just ever so briefly the figure from the IDC manual that Christos showed. Thanks, Christos, for the introduction, because I won't have to go through this in very much detail. But each of these input pipes here are various data streams that come in. And as you see, they all come together to produce a bulletin, but there's an awful lot that happens in the interim here. There's measurements on various waveforms. There's model predictions to hypothesize, for instance, where the event that generated the signals came from, and seeing how well that matches the data. There's an automatic aspect of that that produces these various SEL bulletins. And then an analyst comes along and says, oh, here's some places where there can be some improvement. Sometimes those improvements are quite significant to produce this reviewed event bulletin. And a lot of the technology has to do with improving these various aspects of the system. And one of the first places that I got involved in CTBTO is this regional seismic travel time. And that is, I'll very briefly describe what that is on the left side over here. I won't go through this in detail, but standard seismic models produce a travel time through a spherically symmetric Earth. We developed a model of the Earth's crust and upper mantle. These are the various crustal layers, and this is varying crustal thickness. And then we also incorporated a very simplistic algebraic formulation of the travel time that enables this calculation to be done in a millisecond, which is needed for operational speeds. What this does is this is now distance in degrees. 0 degrees is at the station, and each degree is about 111 kilometers out to about 95 degrees. And then this is the standard deviation of travel time predictions as a function of distance. And before RSTT, we see at these regional distances this large error, and then it ramps down to teleseismic. And the object of RSTT was to develop this model of the crust and upper mantle that controls travel times in this area and bring them down to the level of teleseismic, so that when we incorporate regional data, which lowers monitoring thresholds into the system, we didn't degrade the solution. And here's an example on the right of just how much it can be degraded. This is for the 1998 Indian nuclear test. The known location is here at this pin. If we just use regional data in this area, we get a location that's about 50 kilometers to the south. And importantly, the uncertainty doesn't overlap this because uncertainty ellipses don't take into account bias very well. And these errors are essentially bias. If we use a global network, we get closer. So now we're incorporating data in this area. We get closer but these regional biases still push the location off and the uncertainty ellipse doesn't cover it. But then if we use RSTT with that global network, we get even closer, and importantly, the error ellipse encompasses the known location. So this is just an example of what we did. We provided this to the CTBTO about 10 years ago, and through a series of testing, both by the professionals at the IDC and international experts, we made a lot of modifications. The input from them was crucial in making this more useful. And as Megan said, it's now incorporated into the IDC. As we look forward, the kinds of things that we are looking at involve improvements to the system, both in terms of data analysis. We saw a little bit about this, for instance, improved waveform filtering. This is a seismic recording of the first North Korean test at station MDJ. If we do a standard low pass filter that's commonly used for things like waveform analysis of moment tensors, we get a seismogram that looks like this. If we use these new wavelet filters, we can get a very cleaned up signal in one pass. A conventional analyst might get this portion with one filter, this portion with another filter, and this portion with another filter. Typically, this would be this low pass. And in this case, we can just apply this one filter and get a very clean signal. The other thing is measurements on these signals. This is some work from Zhu and Baroza. And we can take a look and get much more accurate measurements of these arrival times that are used for many purposes, most of which is seismic event location. And the better job we do of this up front, the more analysts don't have to adjust these things. And in some cases where the events are clear, the signals are clear, we can do it all in one pass. As I mentioned, there's the data analysis part, and then there's also the predictions from models. So, we have to do hypothesis testing. Event occurred here, well, it matches these observations. Full physics simulations are a large part of that going forward, but oftentimes they're too computationally expensive to use in operations. And I'll show two examples of that. One from our Livermore NARAC group, where they do a full physics wharf lodi calculation to look at deposition from a source here. These is a release into the atmosphere, and then these colors indicate the concentration of deposition. And using various machine learning techniques, we can train it given various atmospheric conditions and the location of the release to say, this is a very fast estimate of what this full physics calculation would be. You can see the details are different, but it gives a good first order. And then for seismic travel times, we can do the same thing. We can train the network, the neural network, to emulate the calculations of a full 3D Earth. Regional, the RSTT is just regional, so out to 20 degrees. In this case, we're looking at a whole Earth model and looking at, in this case, these are the errors of our standard 1D model, and then using machine learning with a full 3D model as a function of distance. These are the travel time prediction errors. So we can improve things and speed this up. This is computationally compatible with an operational system. And then we can also do things like, well, once we have the event location, we can feed these waveforms into a neural network and categorize them. Are they an earthquake? Are they an explosion? And it uses various parts of the waveform. And at this point, we can get about 90% accuracy on a trained data set. This is a little bit more bleeding edge at this point. So this is not something that I would generally use in ops right now, but this is just a look forward on the kind of thing we're doing. And I'll stop there and leave time for my other panelists.
All right, thank you, Steve. And another great look at some of the things where we've already made significant improvements. I don't think I'd seen that picture before of the India test and seeing really the effect that having accurate regional travel times makes. That was a really impactful picture to see that more data, more crappy data, more bad data doesn't help things. More good data helps things. So a good thing for us to keep in mind in this discussion in general. I think next I will turn the attention to Claire and then Nimar. And I'd like to ask you guys from your perspectives, What new approaches do you see emerging, even from other domains, that might be beneficial in this work? Claire, let's start with you. I think you're muted still.
It's okay now. Thank you for reminding me. I have several ideas, but they all are the same. They all are in order to dissect the seismogram, in order to extract more information, to better understand which wave we are, and in order to afterwards are able to use this information to improve, for example, event characterization or etc. And all these aspects are mainly of using, the first one is using the three-component array processing, because it's my research of area. And because with three-component array, we can have theoretically information of both propagation and polarization, and both information are quite interesting. And in this, I want to mention there are two people, Martin Gall from Australia and Katrin Lohr from Germany, and they both apply three-component FK analysis by doing a grid search over propagation and polarization. I think this study was quite interesting because they estimate both at the same time, so they want to extract both information. Even if their approach may be quite consuming, but I think the idea is quite good, and this there's such a thing that you can have a look at it. The second one is maybe how to improve the waveform, and one idea could be just to do some principal component analysis in order to just project the waveform orthogonally to an identified noise. For example, if you know that you always have a noise in one direction, and you want to, and if you have another event of interest which come from which arrive at the same time as this noise, sometimes it's not well characterized. So that's another idea. And in the same way, we can. It's not new, but it's not really applied. It's also some multi-source aspect. It's the same idea of if you have several identified noise, or if you have two waves which arrive at the same time with the current IDC with PMCC, for example, you only detect one wave at a time for one frequency, and one time and one frequency you can only see one wave. So this aspect could be also maybe not in automatic way, but in order to review some events. Yes, this is yeah. I don't know. I think it's just general view, but
Yeah, no, that's great. As you're talking, I'm thinking about what Paul Richards was saying in his talk too, about going from using tiny bits of information from the lowest amplitude part of the signal to using the full richness of the waveform. And all the things you talked about were really about different ways we can get to that full richness of the waveform and use like everything we have there, and multiple sources and combining them, and what can we add when we put it together rather than these just little pieces of information. So there's a wonderful list of approaches to consider. Nimar, let's take this question to you.
Thank you, Megan. I think before I address your question, I want to address a few comments on data. So in general, my personal belief is all data is good, even if it's crappy data. And anytime a scientist says that, we want to drop data and we get better results, like I heard someone said before, my ears get this. I think that that's a sign that there is something in the model of the data that is missing. the way I see about it, I mean, let me give you a more real world perspective. Say we had an extra eye in the back of our head and it was completely blurred and we could hardly see from it, right? But still we had an extra eye and it was giving you some signal. I'm sure we would all agree that we can get a much better awareness of our surroundings with an extra eye, even if it's a crappy eye. So the point really is, as long as we understand what the data is and understand its limitation, I have a good definition of what is good, what is crappy, and we account for that in our statistical models, we can use any amounts of data. I think that that should never be a concern. But coming back to your question of where we have seen improvements, I mean, obviously, I would like to talk about the work that that I have worked with my co-authors on building Bayesian models for event location or for event identification that an event did exist in the first place. Been very fortunate to have been supported by the CTBTO community for the last decade and more on some of the work that we have been doing. And I think in terms of building Bayesian models of event formation at a global scale, some of our recent work has shown that we can definitely get results comparable or even better than human analysts, especially when we compare the results to regional bulletins. The differences that we find that are remaining are in terms of missing events that were built by analysts by hand in terms of being able to better locate the arrival times of detections or even to find detections that were missing from automatic analysis. So those are the kinds of events that are kind of very hard to build automatically. But it's encouraging a lot of the work that is going on in the deep learning applications in seismology. I think some of the work by Dr. Barroza and Musavi and others that were cited by Christos are very, very relevant. And they have shown that these problems of seismic detections, phase identification, even arrival time calibration, the arrival net project or the back azimuth calculations can be improved a lot with deep learning. Although I would caution that a lot of the work that is happening in the scientific community is not directly applicable to the CTBTO domain, especially because of the work by Barroza and Musavi and others. They're focused more on regional detections, like within a few hundred kilometers. And they work very well, fantastically well at those distances. The question is, do they work at larger scales is an open question. One of my co-authors is presenting tomorrow is trying to address some of those questions for discrimination problem at teleseismic distances, like not 200, that's 20,000 or 80,000 kilometers away, right? And that's kind of where things get more interesting. Maybe I got an extra zero there. I meant more like the 20 degrees or 60 degrees away. So 6,000 kilometers away. Right. So I think so. There's some very interesting work to be seen in taking the work that is happening in the scientific domain, which is very, very regional focus, and bringing it into the CTBTO domain, which would be very exciting going forward.
Yeah, fantastic point. I've also been very fascinated by the work coming out of the Barroza group. That's a Stanford team for those of you that may not be familiar yet with their work, and they've done some very interesting stuff. So I'm glad to hear there's a talk tomorrow about it from your coworker. I think Rigo TB from Sandia has also been looking at that. A lot of it comes from using things from the music world and applying that to our world, and it's very interesting work for those of you who want to look at something. Let's take these ideas, which you guys both mentioned, these neat areas of where there's growth and progress. And I want to go back to Harry and then ask, where do you think there's still room for improvement? If I was a early career researcher, where would you advise me to focus my time? Where does the CTBTO still need attention and help?
Thanks, Megan. I'm glad to talk about that. I may have presented the impression that, gee, this is all worked out. We just need to nail a few details and QA the software and it's ready to go. And that's not really true. we have a lot of things between us and implementation, and some of them are still pretty conceptual. So I have 4 questions here that need to be answered. One is how can we fuse xenon and aerosol measurements? I mean, we know in principle how to do this. They're both transmitted in the atmosphere, and that can be modeled with atmospheric transport calculations, but they behave very differently in the atmosphere, and that may require that we do different kind of simulations than are done today by the IDC. The next question is how can we take the radionuclide background into account? A number of talks yesterday were about xenon backgrounds and how to take them into account. And we see through these ATM challenges that people are doing and the work that's in the NDC preparedness exercises that they're rapidly getting better, and so much better than that first image that I showed before, where people complain that you're off by 50% or something, where it used to be like astrophysics, where you wanted to have the right number of zeros in the answer. So taking the background into account, there's a lot of work to be done there. I can see fleets of grad students working on this problem. Next, how do we make use of isotopic ratios? We don't always have 2 isotopes, but if we do, how could we use that in an automated way in a screening tool? That would be great. And there's been some stuff presented at S&Ts before where people are beginning to work on this problem. It's not completed. And then my favorite one, which I think sort of circles back to something that Nimar was just saying a moment ago, how can we automatically generate a list of associated measurements? As I was trying to explain, that some of the measurements we have are not related, and by adding them into a calculation, you make your calculation worse. So just because they're not related. So I didn't mean to say that some data was bad. It's just not germane. But how can we do this? It's done through a thing called well, originally a thing called global association for the seismic world, and I think NetVisa is something that has replaced that. But in any case, the PhD student that comes up with a scheme for global association for radionuclides, will, as also happened to Froda, be attached to the CTBTO for decades after that. It will be a massive improvement if we had a global, an automated and objective way to find the measurements that are all associated with a given event. So that's my take. Plenty of work to do.
That was a fantastic list. I'm actually going to suggest that after we're done with this panel and you can go to super events and type in the chat there, I would request that you actually put those questions there, because I think they would be very useful to have that collected where people can see it again. I'm going to turn the same question now to Steve, who can answer it more from a seismology or waveform perspective. Where do you think the areas are where there's still a lot of room for improvement? If you were an early career scientist, where would you focus your efforts?
So I think the first thing to say is that CTBT, the IDC, has a very robust system at this point. It works, and I would recommend that any young scientists familiarize themselves with what's been done. A lot of the new ideas we're seeing here were actually envisioned 20, 30 years ago. It's just we didn't have the computational resources to make them real. I would suggest reading some of, and a lot of this is captured in the IDC documentation. I would become familiar with that. And then I would start to look at what the new topics of research are. And some of those have been covered today. So there's the measurement side. We have these signals coming in and we do measurements on them. And sometimes those measurements, because there's a huge volume of data coming in, those measurements aren't always done exquisitely. So ways to improve the efficiency and accuracy of those measurements is hugely important. The other side is, as I said, we have to then match those observations to what we predict in our models And that's where we get our bulletins from that the CTBT is mandated to produce. So then, we need to improve those models so that they are more accurate, and we need to make them usable in an operational system. If people like me at a national lab who have huge computational resources at our disposal, we often, say, okay, well, we just do this full physics calculation, look at that, voila, and I can get a great answer. But in an operational system, you can't devote one of the world's fastest computers to day-to-day operations. So we need to make this thing fast, a fast calculation, so that it can be used in real time. So those are just some of the areas that I think are really promising and should be pursued. The other thing I'll say is that oftentimes these methods need extensive testing. Robustness is of the utmost importance. If it produces an exquisite solution 80% of the time and something that is difficult to understand 20% of the time, that's really something that you'd have to consider. A 99% solution that's very, very good is often the best answer. I'll stop there. Thanks.
Yeah, I think that's a good point. That sometimes we need reliability almost more than anything. I'm seeing lots of questions start to come in. Some of these I'm going to save for a little bit because I think we're going to touch on things related to them, but keep sending in the questions. So I am getting them and I am seeing them. I want to talk now a little bit more about these questions about data and go to Claire and ask her a little bit to talk a little bit about what makes CTBTO data difficult. Where are the ways sometimes where standard procedures maybe don't work for us, or this particular challenges of our data world?
So can you hear me? So, yes, CTBTO data are sometimes quite difficult. First of all, because you have many data, so you need to manage all of this data, and also because there's a difference between the theory and the real life, and when you have a waveform, it's always more complicated as expected, and particularly for ACE wave, because because sometimes you can see it in the waveform because you have an amplitude, so you expect to have ACE wave, but when you are looking at the coherency, when you want to detect ACE wave with a reprocessing, for example, sometimes it's quite difficult, because ACE wave are less coherent than P wave, but also because for local and regional events, ACE wave arrive in the same time as a coda P. So sometimes maybe it's explained also why it's less coherent. So sometimes you didn't succeed. You have you have amplitude, but you didn't succeed to detect it. That's explain why sometimes it's difficult, but also because you have plenty of because you record a lot of things, not only your event and interest. You also have a lot of noise, which record at the same time, and you have to distinguish between this noise and your event of interest. And to this both aspect, maybe from our side, I think that we can make some improvement in the measurement part. So, for example, if you want to detect even better the ACE wave, for sure you need to look at the horizontal components, because when you investigate only the vertical components, it's only provide you the top frame, and you miss seismic wave which are in the horizontal components, such as low wave, but also SH wave, but even P wave. for example, if you have a look of my presentation from this morning on the example I give, the P wave where you have better signal to the noise ratio even for the P wave on the radial component than the vertical. So this some idea, but also I mentioned before that we have no, sorry, everything. I have a lot of things in my mind. Sorry, I try to. Another idea also what's in and another example to illustrate why CTBTO data are difficult, is also because now we have a way which are more and more incoherent. We have good data, but sometimes you detect too much, and so sometimes you have permanent detection, and then when you try to make some classification, when you try to make some family, you just merge different, you merge an event with from noise because you're coming from the same azimuth with more or less similar velocity, but we miss some event. And I think this is a this I don't have any other idea.
No, that's a good summary of the challenges of this. I think almost all of us can recall some of those moments where theory met reality and things didn't work as expected when we were first working with data. I can certainly say for me, coming from a sort of theoretical background, my first encounters with seismic data were sometimes a little bit challenging because everything was not quite as perfect as I expected. I got a question in, which also is related to this topic. So I think this one, maybe I'll give this to Nima. I think you'll like this one. This question says, from Kurt Unger, it says, all data says something about something, often many things. Oops, new questions coming in and it slid off my screen. Let me try this again. All data says something about something, often many things. How do you account practically for true information content versus red herrings?
That's a great point. I think without going into generalities into general domains, we can talk about specific examples in the seismology domain, which might be more relevant to this audience. So I can give an example. I think there's a question also about CODA detections. So early on when we were building this process, what we found is that we were creating a very large number of false split events. And over time, we looked at that and we were told, hey, that's because you often have these detections in the CODA, which are unexplained by standard seismic phases. And if you just take everything in, you will create these split events. It's a well-understood problem. And the standard way to solve it is just to drop detections that come within a few seconds of each other or within 30 seconds or something like that, right? There were some standard techniques. And we applied that and it gave us what we wanted. It avoided these split events that we were forming. But of course, that was the wrong thing to do because we were dropping data. Like I said, we should never drop data. A statistician should never drop, they should try to explain the data. And even so the question I went back to the seismologist who had told me to drop that data was, okay, well, can we really understand the physical processes behind these CODA detections? What do we know about them? What can you tell us about the distribution and how they're related to the actual arrival? And based on some discussions, and we built a parametric model of that. And we said, okay, we will keep these as detections, but we will simply expand the hypothesis space to include CODA as a possible categorization of events and explain them with the generative model. It took a lot more work. I mean, it took another 6 months just for explaining one small thing in the detection, which I'm sure if you read the paper on NetVisa, you will probably not even notice because it's a small paragraph there. But what that did is we were able to keep all the detections, and we got rid of the split events, of course, but then we found out that in some cases, by not discarding these so-called coda, we were actually forming additional events because they were real, and just doing a simple labeling, or even just applying a neural network-based labeling of what is coda, what is not coda, can have 10% inaccuracy, and there you can start to lose real events. And so, yeah, I think, again, without going into generalities of what the questioner is thinking of as a red herring, and I would suggest that just build a model of exactly what you are seeing, because there's always an explanation. I mean, we understand it, we choose, and I would not want to use a strong word like we are lazy, but at some level, all scientists are lazy up to some degree, in the sense that at some point we have to stop and say, okay, we've done enough with this thing. And I think the question of what we call data, red herring data, it's just us being lazy at some level and saying, okay, I'm going to stop modeling here and I'm going to stop explaining it. And maybe that is a fine thing to do. I mean, I've had to do that too in many domains, I'll be honest, where at some point I've had to be lazy and say, I really don't have the ability to spend another year on just explaining this small portion of this data, and then we'll just have to drop it at that point. And that's kind of where the border exists. So I'm not going to be a fundamentalist and say never drop it, but I think it's sometimes one has to be pragmatic. But
Well, very, very insightful thoughts. I'm going to take that, and I think it kind of works well to lead into the next question I had planned. So we'll stick with you, Nima, and then we'll go to Steve. And how should we go about introducing new data analysis approaches at the IDC? In particular, how do we go about testing things reliably? And when can we begin to rely on a new method? When can we begin to trust it? So we'll start.
that's a great. Sorry, that's a great question, Megan. I can turn this question back to you. When can you start relying on NetVisa exclusively at IDC?
Well, not the first 10 years.
Right, not the first 10 years. By the way, that was a great analogy that Harry gave about Frodo's ring and being attached to it. Like you're well aware, I've been working for the CTBTO since 2009. And I think I have been answering this question every year. What additional tests have to be done to answer the question that a new method is reliable? In that sense, I mean, initially, of course, the results were not so good, and we had to add a lot more models. So it was a pretty straightforward question: go back and do more research. But at some point, in 2012, 2013, we were at a phase where we could get better results than existing system, and better than analysts in many of the cases. But the question in the CTBTO context, because there are a lot of stakeholders, and because the stakes are so high in general, that one has to, that any new method, I mean, you can of course put it in a pipeline, you can, you can do results, you have offline data, you can even show them to human analysts and do that kind of analysis and present them in meeting after meeting, all of that. But one has to really be open to the critical questions that will get asked about the work. I think that's where the real interesting work happens, when the critical questions about what are the biases of this work, what happens if you remove this part of the model, like Steve was asking about the model the other day. What happens if you remove each part of the model? What exactly does each step in your processing contribute to the overall thing? How will it change it? How will it change the workload of the analyst? So there are just a few questions. I think over the last 10 years, I have found that the more testing we did, the more questions that were raised. And so every few years there was, and in fact, every year there were like 2 or 3 new questions that the stakeholders had not thought about before. But then as we answered previous questions, as we got more and more data, the number of questions kept increasing. And of course, they eventually, tapered off and died down. And as we got a lot more help, especially IDC personnel who did a lot of the testing. But I think anybody who is trying to deploy a new system at the IDC, I don't want to use the word they should be forewarned, but they should be prepared that they are putting on this, they're putting on the ring. And and if they wish to see it through, I should point out though that in that first 2009 session, there were multiple other brilliant researchers in AI who applied some of their methods here, and they got much better results than some of the work that I had gotten. But I think the some of that work did not see it through, even though they were very compelling results. And the problem is that the testing regime is very rigorous at the IDC, and going through with it, collecting all the data, understanding it, and then communicating the work takes a fair amount of time and energy and patience. So I'll leave it at that.
No, I think that's great. And we're definitely laughing as we think about Nimar's journey. But I think I will also say he was in many ways one of the front runners of this. So we grew as he grew in a way. So now for somebody coming in, we can give you a much better list of questions ahead of time of all the things that we'll need to know. I think it's always good if you can show, if you could ideally first reproduce what we are getting. That's always a fantastic spot. Sometimes that's of course not possible, but really at least understand what we're currently getting, and then look at measuring how does yours improve things? How does it impact the analyst? How does it impact the results at each stage of processing? How do you really trust things? Because we are fundamentally a very conservative organization where we cannot miss something of importance. And so be prepared as you're thinking about your tests to think about how am I going to make sure that I can show people that we will not miss something of importance. So just a few thoughts. I'm sure Steve has a few more because he's also been through this process with RSTT. So let's see what you can add to the conversation.
Thanks, Megan. And I'll just underscore everything that Nimar said and add to it because I agree with everything Nimar said in terms of having to see things through. But I think the main underlying notion here is that any method that is introduced at the IDC has to work on all data. And during the testing process, if someone proposes that their method be used at the IDC, you can bet that it will be tested with every single bit of data. You might say that in the past I threw away this data because that's just not very good. Getting back to Nimar's point, it has to work on it. You know, you can't just say, well, it works in almost all cases. It has to work in all cases. The other thing I'll underscore is that CTBT is an international agreement, and it's an international agreement amongst states parties. So any technology that goes into the system has to be transparent and understandable by the monitoring community. It's difficult to say I've got this black box that gives you the right answer, because all of these states parties have to say, well, I have to understand how it works. The other thing is that circling back to this testing, you might say you've tested it all in all data, but as you give it to the IDC, it will be tested by the IDC staff and researchers in the international community, both academically and professionals who are involved in the monitoring community. They're going to test this on data that you may have never seen before. So, and that kind of information has to be folded back in. And just to underscore one last thing, robustness is so key. It has to be able to work on all the data and produce a result that is better than the current system. And that can be through that. A better can mean more accurate, or it can mean more efficient. Both of those things are tremendously important. And Megan, I'll turn it back to you.
A great point about robustness and accuracy and efficiency. I think I would say if you really want the chance to, do a thorough job of validating your method and getting good at presenting it and clarifying it and asking these deep questions, come work with us because we'll take you through that whole process. I've got some good questions coming in or comments coming in, and that I think I'll read. First, I'll read this one. I think one of the most important problems to be addressed with using machine learning methods in an operational pipeline is addressing uncertainty estimation. Machine learning methods can produce incredible results, for example, 95% accuracy. But when they fail, we need the uncertainty estimates to reflect that the result is dubious. And I'm going to say that again. We need the uncertainty estimates to reflect that the result is dubious. This is important, particularly important for nuclear monitoring, where the events we are looking for represent less than 1% of the total events. Accidentally screening out a nuclear explosion is a disaster, even if you correctly screen out many earthquakes. And I thought this comment made two really good points. The importance of uncertainty estimates. I think this is a theme that keeps coming up in this whole S&T, is the importance of uncertainty estimates. And the fact that we sometimes don't have a lot of training data because we don't have that many examples of nuclear explosions. So all of that makes good. So the first thing about uncertainty gives you an idea of some of the testing and the questions that you're likely to get if you pursue this path. And then the comment about not having a lot of training data, I think is also one. Nima, do you have additional comments, or Steve, or anyone really on working with our data when we don't have so much data that's an example of what we're looking for?
I'll just very briefly say the IMS, International Monitoring System data, is arguably some of the best curated and highest quality data in the world.
That
it is a very excellent benchmark, but of course it's not perfect. And if I was to point to any one challenge for a new researcher in this area, it's that the network is, by today's standards, relatively sparse. The interstation distance is on the order of 1,000 kilometers or so. Many young researchers are used to these incredibly dense deployments where you can see in seismology the wave field evolve over the network. Whereas in the CTBT, often you just get one time series of ground motion, a seismogram, and you're supposed to be able to say, okay, what was the event? Where was it? So these are some of the challenges of working with the IDC. And just going back to the comment, uncertainty, I think I heard uncertainty is really important. Looking for, not throwing away the nuclear explosion because your receiver operator curve allows it. I would just say yes, yes, and yes to everything else the commenter mentioned. Thanks.
I would like to just add a little bit more about the uncertainty on nuclear explosions. I think what I have seen, my experience with working with all the data here, is that there's a certain amount of hesitation to put an uncertainty estimate on things which could be wrong. So, for example, analysts will often not put depth estimates. They will, if there is some uncertainty, they would just say, okay, this is a surface event. The bias towards making the most conservative choice is pretty clear, and that's perhaps for good reasons. Now, working in uncertainty, I mean, we would ideally like to assign uncertainties to everything and be able to score them and to calibrate them. But I think there's a certain amount of bias which prevents a accurate calibration and measurement of that. So, for example, for depth estimates, we compared to ISC's curated data, and we could talk about the uncertainty of our depth estimates. We could not do that with IMS data. It's not possible because of the aforementioned reasons. But yes, I think I agree that uncertainty estimates should be given for everything, and these are very big, hard challenges. Like we presented, I think yesterday, was that for location uncertainty, even knowing that an event occurs, forget if it's a nuclear or earthquakes, within the 90% confidence ellipse, currently we get only 45% of the events. And this is irrespective of what we are doing. It's even the same thing with the human analysts, the reviewed bulletins as well. And that is a source for concern, source for further research. I think of it as an uncertainty researcher, that's an opportunity for further research and asking critical questions and identifying the sources of unmodeled error in the model. So that's a good opportunity. But at the same time, I think this I think we should personally. I think we should put a lot more emphasis on putting uncertainty rather than making a hard conservative decision. But it may not be possible to do, as Steve mentioned. The CTBT is a treaty, and there are constraints into how it can operate there as well.
I'm getting lots of good questions sort of in this topic area, so I'm going to stick with this for a little bit longer, and then we'll probably talk a little bit more about the process that was done to integrate NetVisa and RSTT, because I know people want to hear about that, and also about what re-engineering will mean for this process going forward. But first, let's just hang out here a little bit. So another question I got was, perhaps NetVisa can outperform analysts, as Nimar implies, but what is the benchmark? We seldom have ground truth in geophysics. How can these innovative methods address this problem? And this is he says geophysics, and this is true, you know, for all of us in all of the domains that we use here. We rarely have ground truth. So I would like to hear your thoughts on how to develop things with that fundamental challenge.
So I think, sorry, go ahead.
Let's go ahead, Nimar, and others of you want to just raise your hand and indicate to me that you have something to say. I can then call on you in an organized manner.
So I think we are somewhat fortunate in that when we are looking at evaluating our work in CTBTO, we are restricted to a very small subset of seismic stations. So all the methods that we are doing when we're comparing against human analysts, we're talking about any analysis done only through the limits of the IMS network. And many parts of the world have very dense regional networks. And this is a trick I learned 10 years ago from a presentation that Steve had given, that you can compare and you can look at regional networks which have a much deeper knowledge about a particular part of the world. So you can randomly pick, Kazakhstan or Northern Italy or even the US NAIC bulletins for parts of the world that they're very, very well covered, and where seismologists rely upon that part being extremely well covered by regional networks. And then you can ask the very simple question, given the global network and given what the analysts have done with the global network and what you are doing with the same global network, how does it translate to that regional? Of course, I'm sure many people will point out that there are biases here. The global network will be somewhat relatively biased towards where the regional networks are. True. I think we cannot address all of the biases, but talking about raw methods, we can ask those critical questions. Okay, that you found events from the IMS bulletin that the analyst did not find, and these events have been validated by these dense regional networks, wherever those dense regional networks exist. Now, we did not choose them ahead of time. They were just given to us that these are the dense regional networks.
That is a great point and a great technique for doing this. Steve.
Yeah, I just want to say that ground truth and reference events data sets are the unsung hero of monitoring. They take a tremendous amount of effort to put together, and they are used over and over and over again. Those efforts have been generated by the International Seismological Center in the UK, by CTBTO, by academic groups, and I'll just mention that in RSTT, it's become a featured component of CTBTO workshops and training sessions, and a key component of that is to go to various regions around the world and get regional experts together with their data sets, and we ask them to contribute data that could lead to adding to these reference event data sets and ground truth data. And those efforts have really added to the internationally available set of ground truth data that we use for testing. And all of those data go to the publicly available International Seismological Center ground truth database in the UK. And they're used for CTBTO academic studies, and they're extremely important. And I'll just say that we can't get enough of it, especially geographic coverage. Thanks.
Yeah, that's a fantastic point. If somebody would be so kind as to put a link maybe to the ISC in the chat, so that anybody that isn't familiar with that resource yet can become aware. And Chris Young, if you happen to be listening, I think you guys might have a bulletin that would be very beneficial as well, that I believe is public. And if you want to mention that in the chat, that could also be a very helpful thing for all the researchers here. Let me see what other questions I've got. How do you validate machine learning methods for nuclear explosion monitoring? What are the challenges specifically for supervised learning using earthquakes and mine explosions, but no nuclear explosions? Somebody want to take this one? It goes back to this issue of we don't have so many examples of what we're looking for. I think what I would say to this is it definitely is a difficulty, and we can focus on doing a really good job of screening out earthquakes, of identifying mines, but we always have to, whenever we develop those methods, make sure that they're not too big or too trusting in what they screen out. It's a challenge. I don't think I have any brilliant thoughts on how to solve it, though.
Megan, I'll just add to that. I see a lot of innovative methods, especially ones where various methods are used to generate synthetic data, and then they're used for testing. Many of those are perfectly valid, but I would warn people about falling into the circularity trap, where you're generating with a method and then trying to test that method to see whether you can reproduce it. And that is a common trap to fall into.
Yeah, it is definitely one to think ahead to. If you're presenting at Working Group B, how are you going to explain to this collection of world experts on what you did and prove to them that you didn't fall into that trap? So speaking of, oh yeah, Harry, go ahead.
Thanks, Megan. I wanted to chime in a little bit on the circularity thing. Steve and I might even be thinking about the same example where somebody used atmospheric transport calculation to a forward transport calculation to say, here's where my synthetic nuclear signal would be found. Then the next person taking up the challenge takes those locations and uses the exact same code to figure out where it came from. And you can get embarrassingly good results that don't reflect the real world. I was on a PhD committee where a young gentleman had simulated what certain nuclear signals would look like inside of a detector. And then he analyzed, basically using the same physics code to invert and find out what the source of the radioactivity was. And it got embarrassingly large results. So there are ways of making these things a little more realistic, a little more difficult, and more lifelike. In the nuclear world, it's not unreasonable to take a tiny bit of uranium and put it in a reactor and make some fissions, and then create a fake fission product filter. And then you can immediately say, well, what is some unrealistic things about this filter you just created? Well, it didn't have radioactivity leaking through the earth or something like that, acting as a filter to only let certain things out. And so then you're array of isotopes that you have on this filter don't make sense anymore. So, you know, you always have to stop and think, if I'm going to make a synthetic approach to test signal, what do I have to do to make that have some kind of verity? So anyway, that's it.
Great comments, great comment. Let's see, we've got about 15 more minutes or so, so keep sending in those questions. And I've got a comment that just came in that I'll read. This was in response to the question I asked orally to Chris Young. And he says, you might be thinking of 2 reference event bulletins that were made openly available a few years ago. I'll put the link on the chat when we're done. They are each just 2 weeks, but they're very carefully worked by an expert analyst. So they're not ground truth events, but they are like very well processed by an expert analyst. Thousands of events each, all with observable signals picked and associated. So between the ISC resource that Steve mentioned in that one, if you're an early career researcher, I would encourage you to at least be aware of those resources to help you in the seismic world, at least. So let's talk a little bit more about what the process was like. We've implied that it was somewhat challenging, that it involves a lot of questioning, but I want to also remind people that we have made a lot of progress. So Nimar, could you talk briefly about what the process was like going from your idea all the way to the fact that now we do have NetVisa running at the IDC, and just give a brief overview to what that process was like?
Thanks for the question, Megan. And I should, of course, add that despite all the challenges, there were a lot of support from the CTBTO community. Many of the people sitting in this panel here, and many people in the audience, and many other people at IDC, all the way up to Dr. Zerbo himself at various points, have provided support for the NetVisa project. But I can talk a little bit about the journey from my point of view. I think we began in 2009 at the Kresge Forum, where Dr. Ronald Lebras had organized with other IDC people a panel for ML specialists to try and apply various ML methods to the CTBTO domain, and very kindly explained to us by various seismologists who came in and explained the domain to us and how to apply our methods. And I think over the years, there were a lot of opportunities to present our work, to interact with the experts, to show where the progress was going, where the gaps were, and to keep getting these the questions on. I think it took about a few years to get NetVisa to a point, I think about 2011, where we could say, well, yes, this is doing something reasonable, and it's definitely worth investing more time in. And I think about 2013 or so phase, we had the first real analyst test where analysts looked at it and asked their critical questions. And in between, it was presented at IDC a few times and presented at working waveform experts group, where the first real critical questions came in about the kind of biases in the model, the kind of assumptions in the model. And I have to say, those were great questions. They were tough questions to answer nonetheless, but they were great. In fact, I felt like I learned a lot more about statistical modeling by attempting to answer these questions as to the biases, as to why we introduced a prior on a model, because that is a question that almost everybody asks, like, why do you put a prior that this is the distribution of seismic events when we are trying to locate nuclear explosion? And that's a very hard question. It took a lot of years to give a cogent answer to that, to do a lot of experimentation to do that. But so that took a few years of work. And I think we were also very lucky that there was a lot of support at the IDC in terms of deploying a beta version of the NetVisa software, running it continuously year after year after year, and having those results available. And then whenever anything interesting event took place, I should not say we were fortunate to have nuclear explosion testing, but that is a fact. We did have nuclear explosion testing in the last decade where those results were available and the NetVisa results were there. And so analysts could look at it various staff could look at it. This was a completely unannounced test, of course, as none of us had prior knowledge of those, and the systems were running, and those things could be tested and they could be presented at the waveform expert group. And so that was, in a sense, I would hesitate to use the word lucky again for such events, but that made sure that gave a lot of confidence in terms of, well, okay, this does work in situ. It does work for unseen events. And there were a lot of other preparedness exercises that were done by the European agencies, where also the results were quite promising. So I think, like I said, anybody working on this has to be very well prepared for the level of rigorous testing that will go through, and the level of critical questions that will be asked. But yes, I think it took about 8-9 years or so of rigorous testing in different scenarios, completely unprepared scenarios, as well as questions, and in terms of trying to do more experiments to answer these critical questions as to how these results would vary under different scenarios that could not be reproduced naturally in the last 8 years. And those were analyzed and presented. And then, as I said again, that a lot of IDC analysts and a lot of IDC personnel stepped in to do a lot of that, most of that testing in the last 5 years, where it has really shifted over to the IDC, and they have taken a lot of the analysis and research on that, and a lot of the new methods have been developed. I should point out Dr. Noriyuki has taken some of the modeling work and tried to generate simulated events from NetVisa model to try and answer more critical questions in somewhat related domains. And so the interesting applications that have been kind of growing up out of it have been quite nice, and we are looking now to integrate with some of the work by Dr. Joshua Dickey, for example, on BASNet and some of the other work. So I think we are at a point where it is getting really, the synergy is really coming in from different approaches being applied. So that's very exciting. But yeah, that was the journey.
Yeah, thank you. That was a great summary of the journey, and it has been a journey. And then right at the end of there, you said something that I think is actually worth mentioning. And I'm blanking on his name right now, the guy whose work you're integrating into NetVisa right now.
Dr. Joshua Dickey,
Yes,
BASNet.
exactly. This is a neat story, actually, which might be inspiring to some of you working on things. We had him give a brown bag for us in the fall. We were just interested in his work, and we realized, wait a second, we could probably integrate this into NetVisa. So we called up Nima and said, hey, could you do this? And it seemed like, yeah, actually we could, and this would be useful. And they're working on it. And so he may have a much shorter path to seeing his work integrated, because he's riding on all the work that Nimar has already done. So that's a nice story. Here, we happen to be very lucky in this session that our convener, Noriyuki, is one of those people at the IDC who has been very involved in getting NetVisa tested and integrated. Noriyuki, could you spend just a few minutes telling us about what this process was like from your perspective and where we are now with NetVisa?
Megan, can you hear me? I hope so. Yeah, actually, we are implementing the full pipeline of NetVisa in parallel with the GA, the conventional one. And I think that NetVisa is in operational quite soon. But as I think that this is a part of the answer to the discussion had Nima and Steve, but we cannot fully rely on NetVisa, I mean, 100%. But someone will say that NetVisa can miss an event, but the GA can find an event that was missed by NetVisa. So we also try to run the GA in parallel with NetVisa. So somewhat we are on the conventional side. Yeah, then what more or less that's all. Do you have anything that I need to add?
I think you mentioned something really important, actually, which was we're going to be running them in parallel for a little while, at least maybe forever. And that touches on something I wanted to make sure to say today, which was we've been discussing all of this in the tradition, in the world of our current pipeline. But as most of you know, we've been doing quite a lot of development on our RN pipeline, which Hakeem presented earlier today. And we've got this huge re-engineering project going on for our SHI pipeline. And one of the benefits of this work is it's going to make it much, much easier for us to test new things. It will be much more modular. So we have a new algorithm we want to test or a new component, we'll be able to run things in parallel with the current one and compare results much more easily. So that's just a little bit of good news that I want to make sure that all of you really realize that the changes that we are doing here to our pipelines will make them more maintainable, more open source, like all these good things. They will also make them more testable and easier to integrate new things. So that is really, really good news for any researchers out there that are thinking like, I wonder if someday my idea could be used. I think these developments are going to make it much easier for us to test things. We are nearing the end of our session. One of the things I also really wanted to make sure we did was to have time for Steve to describe the process of RSTT and what that's been like for him. And then if there are any other questions, I will go to the last minute questions on the chat. So Steve?
Thanks. So the one commonality between NetVisa and RSTT is that they were both developed to work in operational pipelines. They were not basic research that was then adapted for these pipelines, and it still took a decade to get them into operations. Not to dissuade anybody from wanting to go through this process, but RSTT, for instance, was first developed for the US National Data Center to address this problem of them folding in regional data and getting a poorer location accuracy. And I can tell you, we came to them with very sophisticated solutions, and they basically said, how about a really simple one? And after a lot of negotiation, we said, okay, we'll do what you want to do. And so we developed that. It worked for the US NDC, and then it was offered to CTBT. And I was absolutely amazed by the level of interest and support of both the CTBT and the international community, various national data centers around the world who said, okay, we're going to plug this into our system. We're going to use it on data sets that we've developed. And I can tell you they found things that we didn't ever see before. And it was, so these things really get beat up. They get taken and used in ways that you had never imagined before. And that's a good thing because it makes them much better. And the one place where I will mention where we made significant improvements to RSTT based on feedback was this area of uncertainty. Our uncertainty model was quite rudimentary when we initially gave it to the IDC, and it's become now quite sophisticated and much more representative of the true error. When we compute those error ellipses on the epicenter locations, we're now encompassing a ground truth location at about the expected rate. All of these things are really important for CTBT. And the other aspect that I'll mention is how universal or global the CTBT monitoring system is. It's, as we're looking at nuclear explosion monitoring, it's often really tempting to train your data or to get a great result at historical nuclear test sites. But CTBT is meant to monitor the entire globe, and it has to work where people have examples of, for instance, mine blasts in South America or someplace where there's never been a nuclear test before. And those are the kinds of tests that you can expect if you present a technology to CTBTO. So again, it is a rigorous process. And if you're really interested in how your method or data might apply universally to this monitoring problem, I wouldn't want to discourage you from engaging CTBTO with it and working with them to see whether it can help the monitoring system. Thanks.
Yeah, that's a great comment. And I want to encourage all of you watching this to engage with us here at S&T, and continue to engage with us. We've got 2 minutes, which means we are going to do like 30 seconds from each one of our panelists. Any last minute words of advice or just plain keywords that you want people to remember from this session? So let's be brave. We'll do Nima, Harry, Claire, and Steve. So Nima.
Would encourage everyone working on new methods to find a champion at the IDC to work with you. They will really guide you through. They're very helpful. Thank you.
Yes.
Should I just go ahead? Hi, this is Harry again. The radionuclide business new work will begin where the existing radionuclide pipeline ends. And there's decades of work to catch up and a good model to follow, which is how things have been done in waveforms forever. So I think that's really the growth area for students, PhDs, grad students, whatnot.
Great. Claire.
Hi. So thank you for the invitation for this discussion. And I just want to mention that we can easily integrate the horizontal component in the actual IDC process. I think it's something they can doing easily or even in automatic process, but also for the process of reviewing. So yes, that's so. Thank you again, and
Great. Thank you. And Steve.
I'll mention is that the sky's the limit. There's so many things that could be done. To reiterate, I would recommend that young researchers familiarize themselves with the IDC system, and there's a lot of documentation out there to do it, and take a look and see where there are approximations and things that you think could be done better. And there's so many things that could be done. It's hard to list them all. But indeed, things have to be robust and they have to work in all situations, and the testing system will find them. And I'll just end by saying thanks for the invitation to serve on the panel. It's been a pleasure to be here.
And I will say thank you guys. What a fantastic group of panelists. Such a fun discussion today. And really, to all of you listening, do reach out to us. We want to hear your ideas. We want to know who you are and what you're doing. It's a little bit harder when we can't meet virtually, but go ahead and send us notes within super events. And we really look forward to working with you in the years to come. All right. Thank you all so much. Bye.
Thank you so much.
Muted?